This comparison shows the total built capacity of the U.S. power grid over the last 100 years against the proposed generation capacity currently stalled in the interconnection queue. The legacy grid sits at roughly 1,250 gigawatts. A gigawatt is a unit of electrical power equal to 1 billion watts, typically enough to supply about 750,000 homes. Waiting in line for approval is a backlog exceeding 2,000 gigawatts. This backlog results in immediate paralysis. Proposed energy projects now wait up to 4 years simply to undergo engineering studies to determine if they can connect. Driven by high upgrade costs and delays, this queue suffers an 80% attrition rate. This bottleneck represents a structural collapse of the system's underlying logic, occurring despite the availability of engineering capability and capital. The failure compounds across 3 specific intersecting domains: the physical architecture of the wires, the economic allocation of upgrade costs, and the strict logistics of the global supply chain. The legacy grid is a historical artifact designed by vertically integrated monopolies to operate as a localized hub-and-spoke network, with large coal and nuclear plants sitting in close proximity to the cities they power. The contemporary energy transition demands a topological shift. High-yield renewable resources are geographically constrained. The wind blows strongest in the Midwest, and the sun shines brightest in the Sunbelt. That generated electricity must now be transported over long distances to reach distant urban load centers. Attempting to force modern, decentralized energy through this legacy infrastructure actively breaks the century-old operational logic of the entire system. The legacy system functions as a massive, synchronized machine, maintaining its precise 60 Hz alternating current frequency through physical momentum. Traditional power plants utilize massive, spinning steel turbines that are mechanically locked to the grid. These spinning turbines provide system inertia. System inertia is the physical shock absorber created by the kinetic energy of rotating mass, which resists sudden drops in frequency if a power plant suddenly trips offline. Modern solar panels and wind turbines are inverter-based resources, or IBRs. An IBR is a generation technology that produces direct current and relies on solid-state power electronics to convert it to the grid's alternating current. These systems possess zero physical spinning mass. Retiring heavy, baseload fossil fuel plants and replacing them with IBRs degrades the grid's kinetic inertia. Without that physical momentum, minor frequency disturbances carry a highly elevated probability of triggering cascading blackouts. Beyond the frequency, there is a thermal bottleneck. According to the power loss equation, power loss equals current squared times resistance. The actual capacity of a transmission line is dictated by heat rather than volume. Injecting gigawatts of remote wind power into existing infrastructure pushes the current well past the thermal limits of legacy aluminum and steel cables. The metal physically heats up, expands, and sags toward the ground, which can lead to phase-to-ground faults. Advanced reconductoring provides an immediate physical solution. This involves swapping out legacy cables for advanced conductors that replace heavy steel cores with composite materials like carbon fiber. Because carbon fiber does not expand under extreme heat, utilities can double the electrical capacity on existing transmission towers without spending years permitting new corridors. To solve the inertia problem, operators must deploy grid-forming inverters. These are advanced computers paired with batteries that actively generate local voltage and synthesize the physical momentum lost by retiring coal plants. Bypassing the grid's physical constraints requires re-engineering both the thermodynamics of its cables and the electromagnetics of its frequency. Re-engineering the physical grid requires billions of dollars in capital. To fund these upgrades, utilities operate under a legally protected monopoly economic model governed by state regulators. This equation is the revenue requirement. It dictates exactly how a utility recovers its costs and generates a profit. R is the total revenue the utility is allowed to collect. O covers the daily operating expenses. V minus D represents the value of the utility's physical capital assets, or its rate base, minus depreciation. And R is the guaranteed rate of return authorized by the government. Utilities earn their regulated profit almost exclusively through capital expenditure, expanding the rate base by building physical infrastructure. When a customer installs distributed, decentralized solar, their volumetric energy consumption from the grid drops sharply, starving the utility of the revenue needed to cover its fixed costs. The utility must still pay to maintain the fixed physical infrastructure, the substations and wires, regardless of how much power an individual home draws from the grid. This mathematical deficit triggers the cost-shifting paradox. To recover the authorized revenue, regulators must authorize base rate increases on the remaining non-solar customers to cover the fixed costs of the grid. These higher baseline electricity rates make grid power more expensive, which shortens the payback period for rooftop panels and accelerates consumer defection to solar, worsening the mathematical loop. At the macro level, utilities possess a structural incentive to build long-distance, high-voltage transmission lines. These massive construction projects expand their rate base and guarantee shareholder profit. Vertically integrated monopolies are financially motivated to favor massive centralized infrastructure they can own and profit from, while structurally resisting decentralized energy. This misalignment of incentives has paralyzed the MISO interconnection queue. MISO is the Mid-Continent Independent System Operator, the entity responsible for managing the stability of the regional power grid across the central United States. Today, teralots of renewable projects are stalled waiting for grid access. Because wind and solar technologies possess zero marginal fuel costs, federal tax credits have created a massive gold rush for grid interconnection. This map shows the speculative multiplier in action. Because the grid is congested, developers do not know if connecting their proposed solar farm will cost $5 million or $50 million until the grid operator finishes a multi-year engineering study. Developers treat the queue like a lottery. They intentionally submit multiple speculative applications across different geographic nodes with the intent to build only the single project that receives the cheapest interconnection cost. These phantom projects create a cascading restudy loop. Grid operators model load flow sequentially. When one speculative project withdraws to avoid a massive upgrade bill, it instantly invalidates the baseline engineering assumptions for every project waiting behind it. To break this cycle, regulators issued FERC Order 2023. FERC is the United States agency that regulates the interstate transmission of electricity. This order transitions the grid from a first-come to a strict first-ready model. Order 2023 enforces rigid entry barriers. Developers must demonstrate exclusive physical site control and post progressively escalating financial deposits. If a developer withdraws, they face severe financial penalties designed to purge phantom projects from the ledger. The queue's exponential growth is a rational market reaction to a system where the incentive to build power is entirely decoupled from the physical capacity to transport it. Even when regulatory disputes are resolved and the queue log jams are cleared, the physical supply chain dictates the pace of modernization. The single most critical, expensive, and constrained physical node on the grid is the large power transformer. These transformers face a metallurgical bottleneck. To reverse their magnetic fields 60 times a second without melting, the transformer core requires GOES. Grain-oriented electrical steel is a highly specialized alloy engineered at the microscopic level to align its crystalline structure in a single magnetic direction. The global manufacturing capacity for this specialized steel is heavily constrained. Furthermore, large power transformers are bespoke, labor-intensive engineering projects designed to fit the exact voltage parameters of a specific substation. The manufacturing base is currently experiencing a supercycle demand shock. The grid must absorb the rapid expansion of gigawatt-scale AI data centers at the exact same time it is interconnecting massive utility-scale renewables. Domestic factories cannot meet this demand shock, forcing the U.S. to rely on foreign supply chains for roughly 80% of its large power transformers. Procuring these 400-ton units introduces severe logistical premiums, pushing procurement lead times from 12 months to over 3 years. The macro grid transition, despite billions in federal funding, is ultimately anchored to the global manufacturing limits of a single specialized steel alloy. Resolving these compounding hardware and administrative failures requires looking past the legacy baseline toward a new model of energy distribution. The century-old bargain, centralized monopolies pushing power one way to passive homes, cannot survive the physical and economic pressures of the renewable transition. This requires a structural shift to the distribution system operator, or DSO model. Here, the utility manages a digital energy market rather than owning power plants. Acting as a digital exchange, thousands of distributed resources can now compete directly with traditional infrastructure. This framework allows residential solar panels and electric vehicle batteries to dynamically bid their capacity to resolve physical congestion. If a substation reaches its limit, the DSO pays local batteries to discharge, bypassing the need for a capital-intensive hardware upgrade. The modernization of the grid is currently trapped by a compounding probability of failure across multi-year permitting battles, contested cost sharing, and backlogged steel supply chains. Modernizing the new cables.